Okay, so I tried recording this once and I was having trouble because I was trying to do it outside. My lighter, obviously, I'm not a smoker, so I don't know how to use a lighter in the wind, and I was having trouble. So I am going to try this again inside. So quick introduction here. We know that heat is transferred to liquids extremely quickly, but gases are a lot less conductive, and so heat transfer is going to be a lot slower. So putting heat to a balloon usually is going to pop it immediately, but not today. Hopefully not anyway, because I'm in my bedroom right now. So what you need for this experiment, a balloon or two, water, a lighter, and then something to catch the water. I am probably just going to take you into my bathroom and I will demonstrate over the sink or over the tub kind of what's going on. So our procedure, first we're going to fill a balloon with some water, which I already did. You can see the water in there. And then you add some air into the balloon and then tie it closed. So this is what I was doing outside and recording myself, and this is about as far as I got before I started having trouble with my lighter. So then to demonstrate, you're going to hold the lighter to the balloon, and normally that would pop our balloon, but not today. And you can see it kind of there's kind of a spot on the balloon now. But why did this happen? So heat's being distributed throughout the water in the balloon, and the water is absorbing all of the heat. And it doesn't burst because the rubber doesn't reach a temperature sufficient for it to melt or burn. I mean, that's the blackness that we're seeing. It's also on my hands. So the rubber just is stretched thin so that the heat is quickly transferred into the balloon versus popping the balloon. So when we move the lighter to the top of the balloon where the water isn't touching it, what do we think is going to happen? It's going to pop. I'm going to demonstrate this over my sink. And there it went. And now I have a really big mess. However, what we've learned then in this process is that water has a high heat capacity. So it's going to take a lot of heat and a lot of energy to change the temperature of the water. So this high heat capacity of water is basically due to the fact that it takes a lot of energy to separate water molecules. These physical bonds are extremely strong. So this water has a heat capacity of about 4 times that of air. So it's going to take 4 times as much heat to raise the temperature of a balloon full of water than it would a similar sized balloon filled with air. So as the water-filled balloon was put to the flame here just a second ago, the heat of the flame was easily absorbed through the balloon and into the water. And the water directly above the hot spot rises, cools, and sinks again. So it carries away the heat from that hot spot, which is what we call a convection current. The thin rubber surface that was being heated is cooled by the comparatively large volume of water above it, and this cooling process continues until either all the water in the balloon becomes too hot or until a far more concentrated source of heat is applied to a small area of the balloon, something like maybe a blowtorch. So when an air-filled balloon is placed in a flame, as we just saw, well, not as we just saw, but as we know, it bursts. But air is relatively a poor conductor of heat away from that thin layer of rubber. So as a result, and as we saw, the rubber overheats and the physical bonds holding the rubber polymers together are broken. So thank you very much. Have a good day.